Look up at the night sky on a clear evening, and you will see thousands of stars scattered across the darkness like diamonds on black velvet. Each one of those tiny points of light is a sun, many of them larger and brighter than our own. And behind those visible stars, hidden from our naked eyes, but revealed through the lenses of our most powerful telescopes, lie billions upon billions more. Galaxies stretching in every direction, each one home to hundreds of billions of stars, planets, moons, and mysteries we have only begun to understand. The universe, it seems, is impossibly full, crowded with matter and light and the building blocks of everything we know. But there is a place where this is not true, a place where the rules seem to break down. A place so vast and so impossibly empty that it challenges everything we thought we understood about how the cosmos came to be. We found something hiding in the Boötes Void, and it should not be there. If you are finding this journey through the cosmos relaxing and wonder-filled, please take a moment to like this video and subscribe to Cosmic Drift. We explore the strangest corners of the universe together, and your support helps us continue these voyages into the unknown. To understand what we found and why it matters, we first need to understand the void itself. And to understand the void, we need to step back and look at the universe from a perspective that few of us ever consider. We need to see the cosmos not as a scattering of individual stars and galaxies, but as a structure. Vast, interconnected web of matter that spans the entirety of existence. Imagine, if you will, that you could zoom out from Earth. First, you would see our planet shrinking, becoming a pale blue dot against the blackness of space. Then our solar system would come into view, the sun at its center with the planets orbiting in their ancient dance. Zoom out further and you would see our stellar neighborhood, the nearby stars that make up our corner of the Milky Way. Further still, and the spiral arms of our galaxy would unfold before you, a pinwheel of light containing somewhere between 200 billion and 400 billion stars. But we are not stopping there. We need to zoom out much, much further. As you pull back from the Milky Way, you begin to see that our galaxy is not alone. We are part of what astronomers call the local group, a collection of more than 80 galaxies bound together by gravity. Our nearest large neighbor is the Andromeda Galaxy, a massive spiral some 2.5 million light-years away that is actually moving toward us and will one day merge with the Milky Way in a cosmic collision of truly epic proportions. But that is a story for another time. Zoom out further, and the local group becomes just one small part of a larger structure called the Virgo supercluster. This immense collection of galaxies spans roughly 100 million light-years across and contains at least 100 galaxy groups and clusters. Our local group sits on the outer edge of this supercluster, a small community on the outskirts of a great cosmic city. But even the Virgo supercluster is not the end of the story. In recent years, astronomers have discovered that our supercluster is itself just one lobe of an even larger structure called Laniakea, a name that means immense heaven in Hawaiian. Laniakea contains roughly 100,000 galaxies spread across 500 million light-years of space. Now here is where things get truly interesting. When you zoom out to the scale of Laniakea and beyond, the universe stops looking like a random scattering of galaxies. Instead, a pattern emerges, a structure that astronomers call the cosmic web. Picture a sponge, or perhaps a three-dimensional spider web of unimaginable size. That is what the universe looks like at its larger scales. Galaxies are not distributed evenly throughout space. Instead, they cluster along thin filaments of matter that stretch across billions of light-years. These filaments connect at nodes where galaxy clusters form. Dense concentrations of thousands of galaxies bound together in gravitational embrace. And between these filaments, surrounded by them but containing almost nothing within their boundaries, are the voids. Cosmic voids are the empty spaces in the sponge, the gaps in the web. They are regions of space that contain far fewer galaxies than average, sometimes stretching for hundreds of millions of light years with barely anything inside them. In a sense, voids are the defining feature of the cosmic web. They take up most of the volume of the observable universe. If you were to randomly drop a pin anywhere in the cosmos, you would most likely land in a void, rather than in a region dense with galaxies. Scientists believe that voids formed in the earliest moments after the Big Bang. In those first fractions of a second, the universe was almost perfectly uniform, but not quite. Tiny quantum fluctuations, ripples in the fabric of space-time itself, created regions that were slightly denser than average and regions that were slightly less dense. Over billions of years, gravity went to work on these subtle differences. Denser regions pulled in more and more matter, eventually forming the filaments and clusters we see today. Less dense regions lost their matter to their neighbors, becoming emptier and emptier as the eons passed. This is the standard model of cosmic evolution, and it explains most of what we see when we look out at the universe. The cosmic web, with its filaments and clusters and voids, is exactly what our best theories predict should exist given the conditions we believe were present in the early universe. But the Boötes Void does not fit the model. Not entirely, and that is what makes it so fascinating. The Boötes Void was discovered in 1981 by astronomer Robert Kirshner and his colleagues while they were conducting a survey of the universe's large-scale structure. They were mapping the distribution of galaxies in a region of sky located in the constellation Boötes, which is visible in the northern hemisphere and contains the bright star Arcturus. What they found surprised them. In a region of space approximately 330 million light-years across, there was almost nothing. To put that number in perspective, think about it this way. Light, the fastest thing in the universe, travels at roughly 186,000 miles per second. In 1 year, light covers about 6 trillion miles. The distance from Earth to the nearest star beyond our Sun, Proxima Centauri, is a little over 4 light-years. The Milky Way galaxy is about 100,000 light-years across. The distance to the Andromeda galaxy is 2.5 million light-years. The Boötes Void is 330 million light-years across. If you could somehow travel at the speed of light, it would take you 330 million years to cross from one side of the void to the other. For comparison, 330 million years ago on Earth, the first reptiles were just beginning to evolve. The supercontinent Pangaea had not yet formed. Life had only recently emerged from the oceans onto land. The entire history of dinosaurs, the extinction that wiped them out, the rise of mammals, the evolution of humans, the entirety of human civilization, all of that could happen multiple times over in the time it would take light to traverse this emptiness. The Boötes Void is not just large. It is incomprehensibly, almost impossibly large, and it is almost completely empty. When astronomers first surveyed the void, they found only a handful of galaxies inside its boundaries. For a region of space that size, based on the average density of galaxies in the universe, you would expect to find roughly 2,000 galaxies. Instead, the original surveys found fewer than 100. Later studies have revised that number upward somewhat, but the void remains dramatically underpopulated compared to what it should be. This emptiness posed a problem for cosmologists. According to our understanding of how the universe evolved, voids should not get this big. The process that creates voids, the gradual draining of matter from underdense regions into denser filaments and clusters, works slowly, very slowly. In the 13.8 billion years since the Big Bang, there simply should not have been enough time for a void this large and this empty to form through normal processes. Some scientists propose that the Boötes Void might not be a single structure at all, but rather a collection of smaller voids that happen to line up from our perspective. When you look at a three-dimensional space projected onto a two-dimensional sky, sometimes separate objects can appear to overlap or merge. Perhaps the Boötes Void was an illusion of alignment. Multiple smaller voids stacked behind each other like nested bowls. But subsequent observations ruled out this explanation. Three-dimensional mapping of the region confirmed that the void is real, a genuine spherical bubble of emptiness in the cosmic web. It is not an illusion. It is not a collection of smaller voids masquerading as one. It is a single coherent structure of almost unimaginable dimensions. So how did it form? And what does its existence tell us about the universe? These questions have troubled astronomers for more than 4 decades. Various explanations have been proposed, some mundane and some decidedly less so. The mundane explanations suggest that we simply got lucky, that the Boötes Void represents an unusually extreme example of normal void formation. Perhaps the region started out slightly more underdense than average in the early universe, giving it a head start in emptying out. Perhaps the particular arrangement of nearby filaments and clusters channeled matter away from this region more efficiently than usual. Perhaps, in a universe vast enough to contain countless voids, some of them were bound to be much larger than others simply by chance. This statistical explanation is not entirely satisfying, but it isn't impossible either. The universe is enormous beyond human comprehension. There are billions of cosmic voids scattered throughout the observable universe. If you roll the dice enough times, eventually you will get an extreme result. The Boötes Void might simply be that extreme result, an outlier on the far tail of the probability distribution. But there are other explanations too, stranger ones. And to understand them, we need to talk about what has been found hiding inside this great emptiness. For years after the void was discovered, astronomers assumed it was essentially empty. Not perfectly empty, of course. The few dozen galaxies that had been detected inside its boundaries proved that some matter existed within it. But these galaxies were thought to be scattered randomly throughout the void, lone islands in an ocean of nothing, unremarkable except for their isolation. Then, in 1987, astronomer Greg Aldering discovered something unexpected. While studying the void in greater detail, he found that the galaxies inside it were not distributed randomly at all. They were arranged in a pattern. A tube-shaped structure of galaxies stretched through part of the void like a highway through a desert. This structure was oriented roughly toward the center of the void, as if pointing at something. This discovery was strange enough to generate considerable interest, but it was also difficult to interpret. What could create such a structure? Why would galaxies in a void arrange themselves in a tube rather than spreading out evenly? Was this tube a remnant of some primordial filament that had not fully dissipated? Or was it evidence of something else entirely? Further observations revealed more surprises. The galaxies within the Boötes Void were not just unusually arranged. Some of them were also unusually shaped. astronomers found several examples of what are called starburst galaxies inside the void, galaxies undergoing episodes of intense star formation far above normal levels. This was puzzling because starburst activity is usually triggered by galactic interactions, by close encounters or collisions between galaxies. But the void's galaxies were supposed to be isolated, far from any neighbors. What was triggering their starbursts? Even more intriguing were reports of unusual radio emissions from within the void. In several surveys, astronomers detected radio signals coming from regions of the void where no visible galaxies had been identified. Radio emissions in space can come from many sources, including active galactic nuclei, remnants of supernovae, and clouds of ionized gas. But finding multiple unexplained radio sources in a region supposedly devoid of significant matter was curious indeed. These anomalies accumulated over the years, each one adding another layer of mystery to the Boötes Void. It was not just an empty space. It was an empty space that contained things it should not contain, arranged in patterns that should not exist, exhibiting behaviors that defied easy explanation. And then there was the wall. On the far side of the Boötes Void, astronomers discovered one of the largest known structures in the universe. The Hercules Corona Borealis Great Wall is a massive filament of galaxies that stretches for approximately 10 billion light-years. To put that in perspective, the observable universe is about 93 billion light-years in diameter. The Hercules Corona Borealis Great Wall spans more than 10% of that entire distance. It is so large that light from one end would take 10 billion years to reach the other end, a time span comparable to the age of the universe itself. The relationship between the Boötes Void and this enormous wall is not yet fully understood. Some astronomers believe the wall may have played a role in shaping the void, its massive gravitational influence pulling matter away and contributing to the void's extreme emptiness. Others suggest that both structures may have formed together in the early universe, products of the same primordial conditions that created the cosmic web. But the wall's presence raises an interesting question. If the Boötes Void is bounded on one side by one of the largest structures in the known universe, what else might be lurking at its edges? What other massive structures might be hiding in or around this strange emptiness? This brings us to the concept that has captured the imagination of both scientists and the public: the Great Attractor. The Great Attractor is a gravitational anomaly located roughly 150 to 250 million light-years away in the direction of the constellations Centaurus and Norma. Despite its dramatic name, the Great Attractor is not a single object. It appears to be a concentration of mass, likely a large cluster or supercluster of galaxies that exerts a powerful gravitational pull on everything around it. Our own local group, along with thousands of other galaxies, is being pulled toward the Great Attractor at speeds of several hundred kilometers per second. For decades, the nature of the Great Attractor remained mysterious because it lies in a region of sky obscured by the plane of our own Milky Way galaxy. The gas, dust, and stars of our galactic disk block visible light from the region, making direct observation difficult. Astronomers had to rely on other wavelengths of light, particularly infrared and radio waves, which can penetrate the obscuring material. Recent observations have revealed that the Great Attractor is associated with a massive concentration of galaxies called the Norma cluster. But the gravitational influence we detect is even greater than this cluster alone could produce. Some scientists now believe that the Great Attractor is just part of an even larger structure, a vast concentration of matter that includes multiple galaxy clusters and superclusters. What does this have to do with the Boötes Void? Perhaps more than we initially thought. When astronomers map the motions of galaxies in our region of the universe, they find that everything is flowing. Galaxies are not static. They move through space in response to gravitational influences both near and far. These motions, called peculiar velocities, reveal the distribution of mass in the cosmos. Regions of high mass create gravitational wells that pull galaxies toward them. Regions of low mass, like voids, allow galaxies to flow away from them. The Boötes Void sits in an interesting position relative to these cosmic flows. It is located in a region of space where several large-scale structures meet. The gravitational influences of nearby filaments, clusters, and potentially even the great attractor all play a role in shaping the motions of galaxies in and around the void. Some researchers have suggested that the void's extreme emptiness might be partly explained by its position at a gravitational crossroads, a location where matter was pulled away in multiple directions by competing influences. But others have proposed more exotic explanations, and this is where the mystery of the Boötes Void takes a decidedly speculative turn. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale for classifying civilizations based on their energy consumption. A Type 1 civilization would be capable of harnessing all the energy available on his home planet. A Type 2 civilization would be able to capture all the energy output of its star, perhaps by constructing a massive structure called a Dyson sphere around it. A Type 3 civilization would command the energy resources of an entire galaxy. If a Type 3 civilization existed, what would it look like from the outside? This is a question that some scientists and many science fiction writers have pondered. A civilization that had spread throughout an entire galaxy and harnessed the energy of billions of stars would be virtually godlike by our standards. Its activities might reshape the structure of the galaxy itself. Its presence might be detectable across cosmic distances. Some have speculated that the Boötes Void might be the signature of such a civilization. The argument goes like this: a sufficiently advanced civilization, having expanded throughout its home galaxy, would eventually seek to spread to neighboring galaxies. Over millions or billions of years, it might colonize hundreds, thousands, or even millions of galaxies. As it did so, it would capture the energy of the stars in those galaxies, perhaps enclosing them in Dyson spheres or similar structures. These structures would block visible light from escaping, but would radiate waste heat in the form of infrared radiation. From a distance, a region of space colonized by such a civilization might appear as a void. The galaxies would still be there, but they would be dim, their light absorbed and converted to energy by the civilization's technology. The region would seem empty, not because it lacked matter, but because that matter had been put to use. This idea, sometimes called the Kardashev Type 3 hypothesis for the Boötes Void, is highly speculative. There is no direct evidence that any such civilization exists anywhere in the universe. The infrared emissions that would be expected from such a civilization have not been detected within the Boötes Void, and the much more mundane explanation that the void is simply an extreme example of normal cosmic structure remains entirely plausible. But the hypothesis persists, both in scientific literature and popular imagination, because it raises such fascinating questions. If civilizations can grow to galactic scales, wouldn't at least one of them have done so by now? The universe is 13.8 billion years old. Life on Earth has existed for less than 4 billion years. Human civilization has existed for a mere 10,000 years. If other civilizations arose earlier and had billions of years to expand, what might they have accomplished? This line of thinking connects to one of the greatest unsolved puzzles in science, the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" when discussing the apparent absence of extraterrestrial civilizations. The paradox highlights the tension between the high probability that life exists elsewhere in the universe and the lack of any confirmed evidence for it. The Boötes Void, empty of galaxies but potentially hiding something else, offers a canvas onto which these speculations can be projected. It is probably not the home of an advanced civilization. Almost certainly not. The scientific evidence strongly favors natural explanations for its existence. But the fact that we cannot completely rule out more exotic possibilities keeps the mystery alive. And mystery, in science, is a feature rather than a bug. It is the unknown that drives us forward, that motivates the construction of ever more powerful telescopes and the development of ever more sophisticated theories. The Boötes Void may ultimately turn out to have a perfectly ordinary explanation, or it may reveal something about the universe that we never expected. Either way, the journey of discovery is worth taking. Let us return, then, to the concrete observations. What do we actually know about the anomalies within the void? The tube-shaped structure of galaxies discovered by Aldering has been studied in greater detail over the years. It appears to be a genuine filament, a strand of the cosmic web that penetrates into the void rather than surrounding it. This is unusual, but not unprecedented. Voids are not perfectly spherical, and they do not have sharp boundaries. The interfaces between voids and the surrounding filaments are complex and irregular. A filament extending into a void is unexpected, but not impossible. More interesting are the individual galaxies within the void. Studies have shown that void galaxies tend to be different from galaxies in denser environments. They are generally smaller, bluer, and more actively forming stars. This makes sense from an evolutionary perspective. Galaxies in voids have had fewer interactions with neighbors. They have not undergone the mergers and tidal stripping that shape galaxies in crowded environments. In some ways, void galaxies are more pristine, closer to their original state than galaxies that have been jostled and transformed by cosmic traffic. But the void galaxies in Boötes seem to take this to an extreme. Their isolation is profound. The nearest neighbor for some of these galaxies might be tens of millions of light-years away. They exist in a darkness and emptiness that is difficult for us to imagine. If intelligent beings lived on a planet in one of these void galaxies, their night sky would be far emptier than ours. They might look out at the universe and see almost nothing, just their own galaxy floating alone in an infinite blackness. What would such beings think about the cosmos? Would they assume the universe was mostly empty, unaware of the crowded regions that exist beyond their visibility? Would they struggle to detect the cosmic microwave background radiation, that remnant glow from the Big Bang that tells us so much about the early universe? Would they even conceive of the idea that the universe contained billions of galaxies? Or would their isolation lead them to very different conclusions about the nature of existence? These are philosophical questions, perhaps unanswerable, but they illustrate a deeper point. Our perspective shapes our understanding. We observe the universe from a particular place, a rocky planet orbiting an ordinary star in the outer reaches of an ordinary galaxy. If we lived somewhere else, in a void galaxy, or at the center of a dense cluster, our view of the cosmos would be profoundly different. The questions we ask, the theories we develop, the mysteries that puzzle us would all be shaped by the accident of our location. The Boötes Void reminds us that the universe is not uniform. It has structure, and that structure varies enormously from place to place. The cosmic web is not a metaphor. It is a real feature of the universe at the largest scales, and the voids within it are as much a part of that structure as the filaments and clusters. What else might be hiding in the Boötes Void, waiting to be discovered? Recent surveys using the latest generation of telescopes have begun to fill in some of the gaps in our knowledge. The Sloan Digital Sky Survey, which has mapped millions of galaxies across a large portion of the sky, has provided more detailed information about the distribution of matter in and around the void. Infrared surveys from space telescopes like the Wide Field Infrared Survey Explorer have searched for objects that might be invisible in optical wavelengths but detectable in the infrared. These surveys have not found evidence of a Type 3 civilization or any other exotic phenomenon. What they have found is largely consistent with our expectations, though with some intriguing details. The void contains more galaxies than originally thought, perhaps as many as a few hundred, rather than a few dozen. But this is still far fewer than the roughly 2,000 that would be expected for a region of its size. The galaxies that do exist within the void are spread out in complex patterns. In addition to the tube-shaped filament mentioned earlier, there appear to be smaller chains and clusters of galaxies, as if the void contains a skeletal framework of the cosmic web at much lower density than normal. This suggests that the void is not completely devoid of structure, but rather represents an extremely rarefied version of the normal cosmic environment. One particularly interesting finding involves the dark matter content of the void. Dark matter is the invisible substance that makes up about 27% of the universe by mass. It does not emit or absorb light, but it exerts gravitational influence on visible matter. The cosmic web itself is thought to be shaped primarily by dark matter, with ordinary matter falling into the gravitational wells created by dark matter filaments. If the Boötes Void was simply a region that lost its ordinary matter to surrounding denser regions, you might expect its dark matter content to be closer to average. Dark matter does not interact with normal matter except through gravity, so it would not necessarily be swept away by the same processes. But observations suggest that the void is also underdense in dark matter, not just in ordinary matter. This implies that the void was somehow predisposed to be empty from the very beginning, that its underdensity was imprinted in the initial conditions of the universe itself. This finding connects to the question of primordial fluctuations, the tiny variations in density that existed in the first moments after the Big Bang. These fluctuations were quantum in origin, arising from the inherent uncertainty of the subatomic world during the epoch of inflation. They were then amplified and frozen into the structure of the universe as it expanded. The pattern of these fluctuations determined where matter would eventually gather and where it would eventually thin out. If the Boötes Void corresponds to an unusually extreme primordial underdensity, then its existence tells us something important about the statistics of the early universe. It suggests that the distribution of fluctuations included some very rare extreme values, pushing out to the far tails of what random processes would normally produce. Understanding why this happened, whether it was simple chance or evidence of something more subtle in the physics of inflation, is an active area of research. Some theorists have proposed that regions like the Boötes Void might be connected to larger cosmic structures that extend beyond our observable universe. The observable universe is limited by the distance light has traveled since the Big Bang, about 46 billion light-years in all directions. but the actual universe is almost certainly larger, perhaps infinitely so. The structures we see within our cosmic horizon might be parts of even larger structures that extend beyond it. If this is the case, then the Boötes Void might be just a portion of an even more enormous empty region, one that we can only see a piece of due to our limited perspective. This possibility is essentially untestable with current technology, but it hints at the humbling reality that our view of the cosmos, vast as it seems, represents only a small window on an unimaginably greater whole. There is another angle to consider as well. The Boötes Void and other large cosmic voids may play a role in the mysterious phenomenon known as dark energy. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. It makes up about 68% of the total energy content of the cosmos, but its nature remains almost entirely unknown. One hypothesis is that dark energy is not uniform throughout space, but varies from place to place. If this is true, voids might behave differently from denser regions. They might expand faster, or the apparent acceleration might be stronger or weaker depending on where you observe from. Some researchers have suggested that what we interpret as dark energy might actually be an artifact of our position in the cosmic web, a kind of cosmic parallax that makes the universe appear to be accelerating when the truth is more complicated. The Boötes Void, as one of the largest known voids, would be an ideal laboratory for testing such ideas. If dark energy behaves differently inside voids than in denser regions, we might be able to detect that difference by carefully studying the motions and properties of galaxies within and around the Boötes Void. So far, observations have not revealed any dramatic differences in dark energy behavior between voids and other regions, but the measurements are difficult and the precision required is extreme. Future surveys using next-generation telescopes like the Vera-C, Rubin Observatory and the James Webb Space Telescope may provide the data needed to answer these questions definitively. For now, the Boötes Void remains a puzzle, a great emptiness in the sky that defies easy explanation, a reminder that the universe is full of surprises, even in places where there appears to be nothing at all. But perhaps that is the most profound lesson the void has to teach us. Emptiness is not the same as absence. The void is not truly empty. It contains matter, just far less than average. It contains dark matter, shaping the gravitational landscape. It contains space itself, stretching and expanding as the universe grows. And it contains mystery, unanswered questions that drive us to look deeper and think harder about the nature of existence. In the void, we find not nothing, but a different kind of something. A negative space that defines the positive structures around it. A silence that gives meaning to the cosmic symphony. A darkness that makes the light more precious. And there, hidden within that darkness, we found something that should not be there. Not a civilization as far as we know. Not a cosmic anomaly that breaks the laws of physics. Just a handful of galaxies, a wispy filament of matter, traces of structure in a region that was supposed to be structureless. Evidence that even in the emptiest reaches of the cosmos, the universe finds ways to surprise us. What happens when you peer deeper into the void? When you train the most powerful instruments ever built on a region of space where almost nothing should exist? You begin to see things you never expected. You begin to understand that the universe has layers and that emptiness itself has texture. Let us journey further into the Boötes Void and explore what modern astronomy has revealed about this strange place. The first thing to understand is scale. We have talked about numbers, about hundreds of millions of light years, about thousands of missing galaxies, but numbers can only convey so much. To truly grasp the scale of the Boötes Void, we need to imagine ourselves inside it. Picture yourself on a planet in one of the void's sparse galaxies. You step outside on a clear night and look up at the sky. What do you see? If you lived on Earth, you would see the Milky Way stretching across the heavens, a river of light composed of billions of stars in our own galaxy. You would see the occasional smudge of a neighboring galaxy, Andromeda, perhaps visible to the naked eye as a faint, elongated glow. Oh, you would see thousands of individual stars, each one a sun, with its own potential for planets and moons, and perhaps life. But in the Boötes Void, the sky would be far darker. Your own galaxy would still be there, of course, spread above you in whatever form it takes. But beyond it, the universe would seem to end. No neighboring galaxies visible to the naked eye. No smudges of light hinting at cosmic companions. Just your galaxy, alone in an immensity of black. This isolation is not just visual. It has profound physical implications. Galaxies evolve partly through their interactions with other galaxies. When two galaxies pass close to each other, their mutual gravitational pull can distort their shapes, trigger bursts of star formation, and eventually lead to mergers that create entirely new galaxies. The Milky Way has gone through such encounters multiple times in its history, and the remnants of those events are written in the orbits of our stars and the streams of stellar debris that loop around our galaxy. Void galaxies experience none of this. They float in splendid isolation, unperturbed by cosmic neighbors. Their evolution is self-contained, driven only by internal processes. In a sense, they represent what a galaxy would be like if left entirely alone, a natural laboratory for understanding galactic evolution in its purest form. Studies of void galaxies have revealed that they tend to be smaller and less massive than galaxies in denser environments. This makes sense. In crowded regions, galaxies can grow by swallowing smaller neighbors, accumulating mass through mergers. Void galaxies cannot do this. They must make do with whatever matter they captured during their initial formation. Void galaxies also tend to be younger in appearance. They contain more gas, the raw material for star formation, and that gas is often forming stars at a vigorous rate. In dense environments, interactions with other galaxies and with the hot gas that pervades galaxy clusters can strip a galaxy of its gas, shutting down star formation. Void galaxies avoid this fate. They retain their gas and continue forming stars long after their cluster-dwelling cousins have gone quiet. The colors of void galaxies tell the same story. Galaxies that are actively forming stars appear blue because hot, young, massive stars shine predominantly in blue wavelengths. Galaxies that have stopped forming stars appear red because their stellar populations are dominated by older, cooler stars. Void galaxies tend to be blue. Dense environment galaxies tend to be red. This color difference is visible even with modest telescopes. If you could somehow travel to the edge of the Boötes Void and look inward, you would see scattered points of blue light, young galaxies still building themselves in the darkness. Looking outward at the dense filaments and clusters, you would see a warmer hue, the ruddy glow of ancient stellar populations. But appearance is not the only thing that differs between void galaxies and their neighbors. Their internal structures are different too. Galaxies in dense environments often have smooth, featureless shapes. They have been stirred and heated by repeated gravitational encounters. Their original structures erased by cosmic violence. Void galaxies, by contrast, often retain more delicate features. Spiral arms remain pristine. Bars at the centers of galaxies, structures that can be disrupted by tidal forces, persist for longer. In a very real sense, void galaxies are living fossils. They preserve information about conditions in the early universe that has been erased elsewhere. By studying them, astronomers can peer back, in time, learning how galaxies looked and behaved before mergers and interactions altered them. The Boötes Void, with its handful of extremely isolated galaxies, represents an extreme case of this phenomenon. Its galaxies are among the most pristine in the observable universe. Whatever we can learn from them about galactic evolution in the absence of environmental effects is magnified by their profound loneliness. Now, let us consider another aspect of the void, its relationship to the cosmic microwave background. The cosmic microwave background, or CMB, is the oldest light in the universe. It was released approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. Before that moment, the universe was a hot, dense plasma, opaque to radiation. After it, space became transparent, and light began its endless journey across the expanding cosmos. The CMB is remarkably uniform. No matter which direction you look, the temperature of this ancient radiation is almost exactly the same, about 2.7 degrees above absolute zero. But there are tiny variations, fluctuations of just a few parts per 100,000, that reveal the structure of the early universe. These fluctuations correspond to the primordial density variations we discussed earlier, the seeds from which all cosmic structure grew. When CMB light passes through a cosmic void, something interesting happens. The light experiences what is called the integrated Sachs-Wolf effect. As it enters the void, the light gains energy by falling into the void's gravitational potential. As it exits, it loses energy by climbing out. In a static universe, these two effects would exactly cancel. The light would emerge unchanged, but our universe is not static. It is expanding, and that expansion is accelerating. In the time it takes the light to cross the void itself has expanded. The gravitational potential has weakened. The light does not lose as much energy climbing out as it gained falling in. It emerges slightly more energetic, slightly blue-shifted compared to light that did not cross the void. This effect is tiny, far smaller than the intrinsic fluctuations in the CMB itself, but in principle, it is detectable. And if a void were large enough, the effect might be significant enough to leave a measurable imprint on the CMB. Astronomers have searched for such an imprint from the Boötes Void and other large voids. The results have been tantalizing, but inconclusive. There does appear to be a slight temperature anomaly in the CMB, in the direction of the Boötes Void, but it is difficult to separate this from other sources of variation. The signal, if it exists, is buried in noise. More intriguing is a different CMB anomaly, known as the cold spot. Located in the southern sky in the direction of the constellation Eridanus, the cold spot is a region of the CMB that is slightly colder than average. It is about 1/70th of a degree cooler than its surroundings, a tiny difference, but statistically significant. For years, the cold spot was a mystery. It was too large and too cold to be easily explained by the normal fluctuations expected in the CMB. Some researchers propose that it might be evidence of exotic physics, perhaps a relic from before the Big Bang, or a sign that our universe had collided with another universe in the distant past. Then, in 2015, a team of astronomers announced that they had found a possible explanation. Directly in front of the cold spot, between us and the CMB, lies an enormous cosmic void. This supervoid, as it has been called, is somewhat smaller than the Boötes Void, but still immense, perhaps 1.8 billion light-years across. The integrated Sachs-Wolf effect from this supervoid could potentially explain some of the cold spot's anomalous temperature. This finding sparked considerable debate. Some calculations suggested that the supervoid was not quite large or empty enough to fully account for the cold spot. Others argued that the alignment between the void and the cold spot might be coincidental. The question remains open. What this debate highlights is the intimate connection between cosmic voids and the largest questions in cosmology. Voids are not just empty spaces to be catalogued and forgotten. They are active players in the cosmic drama, leaving their fingerprints on the oldest light in the universe and potentially revealing secrets about the nature of space, time, and energy. The Boötes Void fits into this picture as one of the most extreme voids known. Its size and emptiness push the limits of what our theories predict. If we could precisely measure its effect on the CMB, we might learn something profound about the expansion history of the universe or the properties of dark energy. Unfortunately, the Boötes Void is located in a part of the sky where such measurements are particularly difficult. Foreground contamination from our own galaxy, variations in the CMB from other sources, and the sheer technical challenges of making such precise observations all conspire to obscure the signal. Future experiments may overcome these obstacles, but for now, the void keeps some of its secrets. Let us turn now to another mystery, one that brings us back to the question of what is hiding in the void. When astronomers survey the sky, they do not just look for galaxies. They also search for the gas that fills the space between galaxies, the so-called intergalactic medium. This gas is extremely tenuous, far more diffuse than the best vacuum we can create in laboratories on Earth. But there is so much of it, spread across such vast volumes, that it actually contains more mass than all the galaxies combined. In most parts of the universe, the intergalactic medium exists in a warm, ionized state. It has been heated by ultraviolet radiation from stars and quasars, and its atoms have been stripped of their electrons. This gas is nearly invisible, detectable only through subtle effects it produces on light passing through it. But in cosmic voids, conditions are different. The gas density is lower, and the sources of ionizing radiation are fewer. As a result, more of the intergalactic medium in voids may be in a cooler, neutral state. This neutral hydrogen gas can absorb certain wavelengths of light, producing distinctive signatures in the spectra of distant objects. Searches for neutral hydrogen in and around the Boötes Void have yielded interesting results. There does appear to be a population of hydrogen clouds within the void, detectable through their absorption of light from background quasars. These clouds are not associated with any visible galaxy. They float freely in the void, remnants of primordial gas that never collapsed into galaxies. The existence of these clouds tells us that the void is not as empty as it first appears. The matter is there, or at least some of it is. It simply never condensed into the bright star-filled structures we call galaxies. Instead, it remains dispersed, dark, and nearly invisible. What caused this gas to remain uncollapsed? In denser regions of the universe, gravity pulls gas together, forming increasingly dense clumps that eventually ignite into stars. Why did this process fail in the void? The answer lies in the delicate balance between gravity and pressure. For gas to collapse, gravity must overcome the pressure that supports it. In denser regions, gravity wins this battle and collapse proceeds. In underdense regions, pressure can maintain an upper hand, preventing the gas from gathering into dense enough clumps to form stars. The Boötes Void was apparently underdense enough, right from the beginning. That much of its gas never reached the tipping point. It expanded with the universe, diluted and cooled, never achieving the critical density needed to birth galaxies. The few galaxies that did form within the void presumably arose from rare local overdensities, small pockets where conditions were just barely favorable for collapse. This picture implies that the void contains far more mass than its visible galaxies suggest. The dark gas, invisible in ordinary optical surveys, may account for a substantial fraction of the matter deficit. When we say the void contains far fewer galaxies than expected, we may be undercounting the matter rather than facing a true absence of material. To test this idea, astronomers have conducted increasingly sensitive surveys of the void in wavelengths where neutral hydrogen can be detected. Radio telescopes, operating at a wavelength of about 21 centimeters, can pick up emission from neutral hydrogen, even in the absence of stars to illuminate it. These surveys are challenging because the signal is weak and the void is vast, but they are beginning to paint a more complete picture. The results suggest that yes, there is more gas in the void than the galaxy counts alone would indicate. The void is not empty. It is merely dark, a sea of diffuse gas that never coalesced into the brilliant islands of stars we call galaxies. This realization changes how we think about voids. They are not holes in the cosmic fabric. They are regions where the fabric is stretched thin, where matter exists, but in a different state than elsewhere. The void is not nothing. It is a different kind of something. And within that something, stranger things may lurk. Let us venture into speculation for a moment. Not wild speculation, but informed speculation grounded in the known laws of physics and the observed properties of the universe. What else might be hiding in the Boötes Void? One possibility is dark matter structures. We have talked about dark matter before, the invisible substance that outweighs ordinary matter by a ratio of roughly 5:1. Dark matter does not interact with light, so we cannot see it directly. We detect it only through its gravitational effects on visible matter. In dense regions of the universe, dark matter forms halos, vast spherical clouds that surround and enfold galaxies. The Milky Way sits at the center of a dark matter halo that extends far beyond the visible stars and gas. These halos were the first structures to form after the Big Bang, and galaxies condensed within them later. In cosmic voids, dark matter halos are smaller and less common. There are simply fewer dense clumps of dark matter to seed galaxy formation. But the dark matter is still there, spread more evenly across the void's volume, and it may be organized into structures that have no visible counterparts. Simulations of cosmic structure formation suggest that voids should contain a network of small dark matter filaments, a kind of miniature cosmic web at much lower density than the larger web of filaments and clusters. These structures would be completely invisible, containing almost no ordinary matter and certainly no stars. They would be ghost structures, traceable only through gravitational effects. Could such structures exist in the Boötes Void? Almost certainly, according to our best models. Whether we could ever detect them is another question entirely. Gravitational lensing, the bending of light from distant sources by intervening mass, might provide a way. If we could map the lensing patterns of galaxies behind the void, we might be able to reconstruct the distribution of dark matter within it, including any hidden structures. Such mapping is extremely difficult with current technology, but it is not impossible in principle. Future space telescopes with larger mirrors and more sensitive detectors might succeed where current instruments fall short. The hidden architecture of the void may eventually be revealed. Another possibility is primordial black holes. These are hypothetical black holes that formed not from the collapse of massive stars, but directly from the dense conditions of the very early universe. If the density fluctuations in the first moments after the Big Bang were extreme enough in some places, those regions might have collapsed directly into black holes before any stars existed. Primordial black holes, if they exist, could range in mass from tiny objects smaller than an atom to giants larger than stars. They would be essentially invisible, detectable only through their gravitational effects or the rare occasions when they interact with nearby matter. Some researchers have proposed that primordial black holes might make up some or all of the dark matter in the universe. This idea has fallen in and out of favor over the years, as various observations have constrained the possible masses and abundances of such objects. Currently, most scientists believe that primordial black holes are not the primary component of dark matter, but they might still exist in smaller numbers. If primordial black holes formed preferentially in certain regions of the early universe, their distribution today might be non-uniform. Could the Boötes Void harbor a population of these ancient black holes, wandering unseen through its emptiness? There is no evidence for or against this possibility. It remains in the realm of speculation, a ghost story for the void. A third possibility involves the nature of dark energy itself. We have mentioned that dark energy is the mysterious force driving the accelerating expansion of the universe. But we do not know what dark energy actually is. It could be a cosmological constant, a fixed property of space itself. It could be a dynamic field that varies over time and space. It could be something else, entirely. Something our current theories have not yet imagined. If dark energy is not uniform but varies from place to place, voids might behave differently from other regions. They might expand faster or slower, or in some other unexpected way. The Boötes Void, as an extreme environment, might show these effects more clearly than ordinary regions. Some alternative theories of gravity predict precisely this kind of variation. Modified gravity theories, developed as alternatives to dark matter and dark energy, sometimes predict that gravity behaves differently in very underdense environments. Testing these predictions requires precise measurements of the expansion rate and galaxy motions in voids, exactly the kind of observations that are becoming possible with new telescopes and surveys. If the Boötes Void shows anomalous behavior, inconsistent with the standard model of cosmology, it could be evidence for new physics. This is perhaps the most exciting possibility of all, though it must be weighed against the more mundane likelihood that the void is simply an extreme but conventional feature of the cosmic web. Let us step back from speculation and return to what we can observe. The Boötes Void is not just a scientific puzzle. It is also a profound meditation on the nature of emptiness and existence. When we look out at the universe, we naturally focus on the bright spots, the stars, the galaxies, the clusters and superclusters that light up the cosmic web. These are the features that catch our eyes and fire our imaginations. They are the places where things happen, where matter congregates and stars are born and die, and new elements are forged in their hearts. But the voids are equally important. They define the structure as much as the filaments do. They are the negative space in the cosmic painting, the silences between the notes of the cosmic symphony. Without the voids, there would be no web, just a uniform soup of matter, without shape or pattern or meaning. The Boötes Void takes this truth and magnifies it. It shows us emptiness on a scale that staggers the imagination. It challenges us to find meaning in absence, to see significance in what is not there. In a sense, the void is a mirror. When we look into it, we see ourselves reflected. Not literally, of course, but philosophically. We are creatures of a small world in a vast cosmos, and we have always wondered about our place in the scheme of things. The void invites us to confront that wonder directly. Are we alone? Is there meaning in the universe? Or is it all just atoms colliding in a void? These are questions that humans have asked since we first looked up at the stars. The Boötes Void does not answer them, but it sharpens them. It makes them more urgent, more personal, more real. Consider the galaxies that do exist within the void. Each one contains billions of stars. Around those stars, planets may orbit. On some of those planets, life might have arisen. If so, what kind of life? What kind of civilizations? What kind of dreams and hopes and fears? If intelligent beings live in the Boötes Void, they might have developed a very different view of the universe than we have. Looking out from their isolated galaxy, they would see almost nothing. They might conclude that the universe was empty, that their galaxy was all there was. They might have no concept of the cosmic web, no knowledge of the billions of galaxies that cluster elsewhere in the cosmos. Or perhaps they would have discovered the truth through patient observation and clever reasoning. Perhaps they would have detected the faint glow of distant galaxies, barely visible against the darkness. Perhaps they would have mapped the cosmic microwave background and deduced that the universe was once dense and hot and structured. Perhaps they would have developed theories of cosmic evolution that explained their isolation as an extreme but comprehensible outcome of natural processes. In that case, they might look out at the void around them, not with despair, but with wonder. They might see their emptiness as a gift, a unique perspective on the cosmos. They might take pride in being the lonely sentinels of the void, observers of a universe they could not touch. This is all fantasy, of course. We have no evidence that any intelligent beings live in the Boötes Void, but the thought experiment illustrates something important. Our view of the universe is shaped by where we are. There is no privileged position, no God's eye view that shows us the truth. We can only see from where we stand. From where we stand, on the outskirts of the Virgo supercluster in a region of moderate density, the void looks strange and empty and mysterious. But the universe is vast, and other perspectives are possible. Somewhere out there, someone might look at our region of space and find it equally strange, equally worthy of wonder. The Boötes Void invites us to practice humility. It reminds us that the universe does not exist for our convenience or comprehension. It is what it is, indifferent to our questions, but generous with its mysteries. We can explore those mysteries, map them, theorize about them, and perhaps someday understand them. But we cannot exhaust them. There will always be more to learn, more to wonder at, more to be humbled by. And in that endless wonder lies the joy of science. Not in having all the answers, but in asking ever better questions. Not in conquering the unknown, but in exploring it with open eyes and curious minds. The void is not a problem to be solved. It is a teacher to be listened to. So listen. Let the void speak to you. Let its silence be eloquent, its emptiness full of meaning. Let us now explore the boundaries of the Boötes Void, those transition zones where emptiness meets abundance. These edges are among the most interesting features of cosmic voids. places where the physics of structure formation plays out in dramatic fashion. Imagine standing at the edge of a great canyon on Earth. On one side, solid ground beneath your feet. On the other, a plunge into emptiness. The boundary is sharp and clear. But cosmic voids are not like canyons. They do not have hard edges. Instead, they fade gradually into the surrounding cosmic web, their boundaries defined statistically rather than geometrically. As you move from the center of the Boötes Void toward its edge, the density of galaxies increases slowly at first, then more rapidly. The first galaxies you encounter might still be somewhat isolated, separated from their nearest neighbors by tens of millions of light years. Further out, the spacing decreases. Galaxies begin to cluster into small groups. The groups merge into filaments. The filaments connect to the great walls and superclusters that define the boundaries of the void. This transition zone is a dynamic place. Matter is flowing out of the void and into the surrounding structures, pulled by their greater gravitational attraction. Galaxies near the edge of the void are not static. They are moving, streaming toward the concentrations of mass that ring the void like mountains surrounding a basin. These peculiar velocities can be measured through their effects on the light that galaxies emit. When a galaxy moves toward us, its light is blue-shifted, compressed to shorter wavelengths. When it moves away, its light is red-shifted, stretched to longer wavelengths. By carefully measuring the spectra of galaxies in and around the void, astronomers can map these flows, revealing the gravitational landscape of the region. Such maps show that the Boötes Void is indeed draining. Galaxies at its edges are falling away from its center, drawn by the mass concentrations that surround it. This is exactly what our theories of cosmic structure formation predict. Voids are not just empty, they are actively emptying, their contents gradually joining the denser structures nearby. But this process takes time, enormous amounts of time. The void has been draining since the earliest epochs of cosmic history, but it still exists today, still largely empty, still defying our intuitions about how matter should be distributed. In a universe 13.8 billion years old, the Boötes Void has not had time to completely empty itself, and it never will, not in the finite future that our best theories predict. This is because the expansion of the universe is accelerating. Driven by dark energy, space itself is stretching at an ever-increasing rate. This stretching works against the gathering of matter. It pulls structures apart, even as gravity tries to pull them together. In the far future, this tension will resolve in favor of expansion. The universe will become increasingly dilute, galaxies drifting apart faster than they can fall together, until eventually each galaxy cluster is an island alone in an infinite sea of darkness. The Boötes Void is, in a sense, a preview of this cosmic future. It shows us what the universe looks like when emptiness wins, when matter is too sparse to form the dense structures we see elsewhere. It is a harbinger of the final state of the cosmos, the great emptiness that awaits everything. But that fate lies unimaginably far in the future, trillions of years from now. In the meantime, the void's boundaries continue their slow dance between emptiness and structure, and astronomers continue to study them with fascination. One of the most striking features of the void's boundary is the Hercules Corona Borealis Great Wall we mentioned earlier. This immense filament of galaxies wraps around part of the void like a mountain range around a desert basin. Its sheer size defies easy comprehension. At 10 billion light-years across, it is so large that light itself takes a significant fraction of the universe's entire age to cross it. The Great Wall raises profound questions about cosmic structure formation. How did such an enormous filament come to be? Is it a single coherency, structure, or a chance alignment of smaller structures that happens to create the appearance of something vast? What role did the void play in shaping its development, and vice versa? Some researchers believe that the void and the wall formed together, products of the same primordial conditions in the early universe. The region that became the void was underdense from the beginning, destined to empty out over cosmic time. The region that became the wall was overdense from the beginning, destined to gather matter and build ever larger structures. They are two sides of the same coin, emptiness and fullness defined by each other. Others suggest a more dynamic relationship. Perhaps the wall's gravitational influence actively shaped the void, pulling matter out of it more efficiently than would otherwise have occurred. Or perhaps the void's expansion pushed matter toward it, the wall, feeding its growth. The interplay between voids and filaments is complex and not fully understood, and the Boötes Void and its neighboring Great Wall represent an extreme case that challenges our models. What we do know is that the boundary between the void and the wall is not a simple transition. It is a region of complex structure, where galaxies exist in a wide range of environments, from near isolation to modest groups, to the outskirts of larger clusters. This variety makes the boundary an ideal laboratory for studying how environment affects galactic evolution. Galaxies at different points along this transition show different properties. Those closer to the void center are bluer, more actively forming stars, more likely to retain their gas. Those closer to the wall are redder, quieter, more likely to have been stripped of gas by interactions with their neighbors. The transition is gradual but measurable, a continuous spectrum of galactic evolution playing out across hundreds of millions of light years. These observations confirm and extend what we learn from void galaxies themselves. Environment matters. Where a galaxy lives shapes what it becomes. The cosmic web is not just a backdrop for galactic evolution. It is an active participant, molding galaxies through gravity and gas dynamics and the endless dance of cosmic structure. Now let us delve deeper into the physics that governs voids. To understand why the Boötes Void exists and why it has the properties it does, we need to explore some of the fundamental principles that shape the universe at its largest scales. The story begins, as all cosmic stories must, with the Big Bang. In the first fractions of a second after the universe came into being, the cosmos was a hot, dense soup of particles and radiation. It was also almost perfectly uniform, with matter and energy distributed evenly throughout space, but not quite perfectly. Tiny fluctuations in density existed even in that primordial state. These fluctuations arose from quantum mechanics, the physics of the very small. On scales far smaller than an atom, the universe was inherently uncertain, its properties not fixed, but probabilistic. This quantum uncertainty imprinted itself on the distribution of matter and energy in the early universe, creating regions that were very slightly denser or less dense than average. In the aftermath of the Big Bang, these tiny fluctuations were amplified by a process called inflation. Inflation was a period of extraordinarily rapid expansion that occurred in the first tiny fraction of a second. During inflation, the universe expanded by a factor of at least 10 to the 26th power, growing from something smaller than an atom to something larger than the observable universe today. This expansion took the tiny quantum fluctuations and stretched them to cosmic scales, transforming microscopic variations into the seeds of all future structure. When inflation ended, the universe contained a pattern of density variations frozen into its fabric. Regions of higher density would eventually become galaxies, clusters, and filaments. Regions of lower density would eventually become voids. The cosmic web was not random. It was predestined, its blueprint written in the quantum noise of the infant universe. Over the next several 100,000 years, the universe cooled and expanded, but the density variations remained. When the cosmic microwave background was released, about 380,000 years after the Big Bang, it carried the imprint of these variations. The tiny temperature differences in the CMB that we measure today are a direct photograph of the primordial fluctuations, a baby picture of the cosmic web. After the CMB was released, gravity began its slow work. Denser regions pulled in matter from their surroundings, growing even denser. Less dense regions lost matter to their neighbors, becoming even less dense. This process, called gravitational instability, is the fundamental mechanism behind all cosmic structure formation. But gravity did not work alone. The expansion of the universe worked against it, stretching space and diluting matter. And after the formation of the first stars and galaxies, other processes came into play. Radiation from stars heated the intergalactic gas, making it harder to collapse. Supernova explosions drove powerful winds that redistributed matter. Galaxy interactions stirred and transformed the cosmic environment. Despite all this complexity, the basic pattern established in the early universe persisted. Dense regions became denser. Sparse regions became sparser. The cosmic web emerged, a network of filaments and clusters surrounding vast empty voids. The Boötes Void is an extreme example of what happens when a region starts out particularly underdense. Its primordial density was lower than average, giving it a head start on emptiness. Over billions of years, it lost matter to its denser neighbors, becoming ever more empty. Today, it stands as one of the most underdense regions in the observable universe, a monument to the power of gravitational instability working on cosmic timescales. But why was this particular region so underdense to begin with? This question takes us back to the statistics of the primordial fluctuations. The fluctuations were random, drawn from a probability distribution that is very close to what mathematicians call a Gaussian or normal distribution. This is the familiar bell curve, where most values cluster near the average and extreme values become increasingly rare. In a Gaussian distribution, there is always some probability of extreme outcomes. Most fluctuations are small, but occasionally you get one that is quite large. The Boötes Void may represent one of these rare large fluctuations, a place where the quantum dice came up unusually low. How rare? That depends on exactly how large and empty the void is, quantities that are still being refined by observations. Current estimates suggest that the Boötes Void is unusual, but not impossibly so. It falls within the range of what our theories predict should occasionally occur. We got lucky, in a sense, or perhaps unlucky, depending on how you think about it. The universe rolled an extreme value, and we happened to be close enough to see it. But there is another possibility. What if the fluctuations in the early universe were not perfectly Gaussian? What if the probability distribution had slightly different properties, making extreme outcomes a bit more common than a pure bell curve would predict? This possibility is of great interest to cosmologists because it could provide clues about the physics of inflation. Different models of inflation predict slightly different distributions of fluctuations. If we can measure the distribution accurately enough, we can test these models and learn more about what happened in that first instant after the Big Bang. The Boötes Void and other extreme cosmic structures are valuable data points in this endeavor. By cataloging the most unusual features of the cosmic web, measuring their properties precisely, and comparing them to theoretical predictions, astronomers can probe the fundamental physics that shape the universe. This brings us to the cutting edge of research on cosmic voids. In recent years, voids have moved from being curiosities to being important cosmological tools. Scientists have realized that voids carry information about dark energy, about the growth rate of cosmic structure, and about possible deviations from standard physics. One powerful technique involves using voids as standard rulers. In cosmology, a standard ruler is an object whose size is known, allowing its distance to be calculated from how big it appears. The most famous standard ruler is the Baryon acoustic oscillation scale, a characteristic length imprinted on the distribution of galaxies by sound waves in the early universe. Voids also have a characteristic size set by the physics of structure formation. By measuring the typical size of voids at different distances, corresponding to different times in cosmic history, astronomers can trace how the universe has expanded. This expansion history is sensitive to dark energy. Different assumptions about dark energy lead to different predictions for how void sizes should evolve. Comparing observations to predictions can constrain the properties of dark energy. The Boötes Void is too large and too nearby to be useful as a standard ruler in this sense. It is a single exceptional object, not part of a statistical ensemble. But studies of more typical voids, those with sizes of tens of millions of light years rather than hundreds of millions, are producing exciting results. They confirm that the expansion of the universe is accelerating, consistent with the presence of dark energy, and they provide independent constraints on dark energy's properties. Another technique involves studying the shapes of voids. In a universe where gravity is the only force acting on large scales, voids should be slightly squashed along the line of sight due to the peculiar velocities of galaxies falling out of them. This effect, called redshift space distortion, can be used to measure how fast cosmic structure is growing. A faster growth rate means more squashing. A slower growth rate means less. Measurements of void shapes are beginning to test our understanding of gravity on the larger scales. So far, the results are consistent with general relativity, Einstein's theory of gravity. But some alternative theories predict slightly different growth rates, which would show up as different amounts of squashing. Future surveys, with larger samples of voids and more precise measurements, will push these tests further. The Boötes Void, again, is too unusual to be directly useful in these statistical analyses, but it serves as an existence proof, showing us how empty a void can get and how large it can grow. It stretches the envelope of what is possible, challenging our theories to explain the extreme. And there is something else the Boötes Void can teach us, something more philosophical than scientific, but no less important. The void reminds us that the universe is not made for us. It does not care about our comfort or comprehension. It simply is, vast and strange and indifferent to human concerns. When we look into the void, we are confronted with our own smallness, our own contingency, our own fragility. This can be terrifying. The void is dark and empty and cold, and it stretches beyond the reach of imagination. To a being like us, evolved on a small warm planet teeming with life and light, the void seems hostile, alien, wrong, but it can also be liberating. The void does not judge us. It does not demand anything from us. It simply presents itself, an invitation to wonder and explore. We can look into the emptiness and see not nothing, but the structure of the cosmos itself. We can trace the faint filaments of matter that thread through the void, the scattered galaxies that cling to existence against all odds, the echoes of the Big Bang that still reverberate through this ancient emptiness. The void is not a negation. It is a possibility. It shows us what the universe can be, what forms matter can take, what configurations of space and time are permitted by the laws of physics. In its emptiness, we find a kind of fullness, a richness of potential that challenges us to see with new eyes. And so we come back to the question that launched this journey. What is hiding in the Boötes Void? The answer, as we have seen, is complicated. There are galaxies hiding there, fewer than expected but not absent. There are dark gas clouds, remnants of primordial material that never ignited into stars. There are filaments of dark matter, invisible scaffolding that shapes the gravitational landscape. There may be primordial black holes, ancient relics of the universe's first moments. There are certainly mysteries, questions that we have not yet answered and perhaps have not yet thought to ask. But perhaps the most important thing hiding in the void is ourselves, our curiosity, our wonder, our determination to understand. When we look into the Boötes Void, we see not just emptiness, but a reflection of our own seeking. We are the universe becoming aware of itself, atoms arranged in such a way that they can contemplate their own origin and destiny. And in that contemplation, the void is not empty at all. It is full of us. Let us now journey even deeper into the mysteries that surround the Boötes Void, exploring the scientific debates and theoretical frameworks that attempt to explain this cosmic enigma. The more we study the void, the more questions emerge, each one opening new avenues of investigation and wonder. Consider the relationship between the void and cosmic time. The universe is not static. It evolves, changes, transforms itself over billions of years. The cosmic structures we see today are not the same as those that existed in the early universe, and they are not the same as those that will exist in the distant future. To understand the Boötes Void fully, we must place it in the context of this cosmic evolution. In the early universe, about 1 billion years after the Big Bang, the cosmic web was just beginning to take shape. Galaxies were forming rapidly, illuminating the darkness with the light of newly born stars. The filaments and clusters that define the web today were still being assembled, matter streaming along gravitational channels toward the nodes where it would eventually gather. At this early time, cosmic voids were smaller and less empty than they are today. The universe had not yet had time to fully sort itself out, to separate the dense from the sparse. Voids existed, but they were shallow depressions in the cosmic density field, rather than the deep basins they would become. Over the following billions of years, the voids deepened. Matter continued to drain out of them, flowing toward the surrounding filaments and clusters. The boundaries between voids and dense regions became more pronounced. The cosmic web sharpened into the network of structures we observe today. The Boötes Void participated in this cosmic evolution, but with a twist. Because it started out more underdense than most regions, it had a head start on emptying. While other voids were still developing, the Boötes Void was already approaching its current state of profound emptiness. It is, in a sense, an old void, one that reached maturity earlier than its peers. This precocious development might explain some of the unusual features we observe within the void. The sparse galaxies that do exist there may have formed earlier than typical void galaxies, giving them more time to evolve. The filamentary structure that threads through the void may be a fossil of an earlier stage of cosmic web formation, preserved by the void's isolation from the violent interactions that reshape structures elsewhere. Looking to the future, the Boötes Void will continue to evolve, though its changes will be slow by human standards. Matter will continue to drain from its boundaries, feeding the growth of nearby filaments and clusters. The void will expand slightly, its edges receding as the sparse galaxies near its periphery fall away. But the accelerating expansion of the universe will prevent the void from emptying completely. At some point, the outward push of dark energy will overcome the inward pull of gravity, and the void will settle into a final, stable state. This future equilibrium lies billions of years away. In the meantime, the void remains dynamic, a living laboratory of cosmic physics. Now let us consider another aspect of the void's mystery, its relationship to the large-scale distribution of matter in the universe. Astronomers have mapped the positions of millions of galaxies across the observable universe. These maps reveal the cosmic web in stunning detail, showing the filaments, clusters, and voids that make up the large-scale structure. But the maps also reveal something unexpected. The distribution of matter is not perfectly uniform even on the largest scales. In standard cosmology, we expect the universe to become more and more uniform as we average over larger and larger volumes. On small scales, matter is highly clustered into stars and galaxies. On larger scales, it smooths out into the cosmic web. On even larger scales, the web itself should average out to a nearly uniform density. But observations suggest that this smoothing may not be complete even on the larger scales we can measure. There appear to be fluctuations in density that persist across hundreds of millions of light years, hints of structure on scales that approach the limits of our surveys. The Boötes Void is one piece of evidence for these large-scale variations. Its existence demonstrates that the universe can be dramatically underdense over regions hundreds of millions of light-years across. While this is consistent with our theories at some level, the void's extreme properties push against the boundaries of what we expect. Some cosmologists have proposed that these large-scale structures might be evidence of new physics. Perhaps the primordial fluctuations had more power on large scales than the standard model predicts. Perhaps there are correlations in the density field that extend across vast distances, imprinted by processes we do not yet understand. Perhaps the universe is less homogeneous than we thought, with variations in its properties that persist to the larger scales. These possibilities remain speculative. The evidence is not strong enough to overturn the standard cosmological model, which has been enormously successful at explaining a wide range of observations. But the Boötes Void and other extreme structures serve as reminders that our understanding is incomplete, that there may be surprises waiting in the data. One particularly intriguing idea involves the concept of the cosmological principle. The cosmological principle states that the universe is homogeneous and isotropic on large scales, meaning it looks the same everywhere and in every direction. This principle is the foundation of modern cosmology. It allows us to use observations of our local region of the universe to make inferences about the universe as a whole. But is the cosmological principle true? On the larger scales we can observe, the universe does appear to be roughly homogeneous and isotropic. The cosmic microwave background is uniform to 1 part in 100,000. The distribution of galaxies, when averaged over sufficient volumes, approaches uniformity. The evidence supports the principle, at least approximately. Yet the existence of structures like the Boötes Void and the Hercules Corona Borealis Great Wall raises questions. How large can a single structure get before it violates the cosmological principle? At what scale does the universe truly become smooth? These are not easy questions to answer, and they touch on fundamental issues in cosmology. Some researchers argue that the largest observed structures are consistent with the cosmological principle if interpreted correctly. Statistical fluctuations, they point out, can produce occasional extreme values without violating the underlying assumption of homogeneity. The Boötes Void may be an outlier, but outliers are expected in any statistical distribution. Others are less certain. They note that the larger structures seem to be larger than what simulations of cosmic structure formation typically produce. If this discrepancy is real, it could indicate that something is missing from our understanding, whether a modification to the primordial fluctuations, a change in how gravity works on large scales, or something else entirely. Resolving this debate will require more data. Future surveys covering larger volumes of the universe with greater precision will provide better maps of the cosmic web. These maps will reveal whether structures like the Boötes Void are truly exceptional, or whether they are part of a pattern that extends to even larger scales. Let us turn now to a different kind of question. What can the Boötes Void tell us about the fate of the universe? Cosmologists have long debated the ultimate destiny of the cosmos. Will the universe expand forever, growing colder and emptier until all structure dissipates into an endless night? Will it eventually stop expanding and collapse back on itself in a big crunch? Or will something else happen, something we have not yet imagined? The answer depends on the properties of dark energy. If dark energy is constant, as the simplest models assume, then the universe will expand forever at an ever-increasing rate. Galaxies will drift apart, the cosmic web will stretch and fade, and the universe will eventually become a cold, dark void. If dark energy varies over time, more exotic fates are possible. Dark energy might grow stronger, eventually tearing apart galaxies, stars, atoms, and space itself in a big rip, or it might weaken, allowing gravity to eventually halt the expansion and reverse it into collapse, or it might do something entirely unexpected, transforming the universe in ways we cannot currently predict. The Boötes Void offers a window into this cosmic destiny. As we have discussed, voids are where the expansion of the universe is least opposed by gravity. They are the regions most sensitive to dark energy's influence. By studying how voids have evolved over cosmic time, astronomers can constrain the properties of dark energy and narrow down the possible futures of the universe. Current observations suggest that dark energy is close to constant, consistent with Einstein's cosmological constant. This points toward a future of eternal expansion and eventual heat death, a universe that gradually runs down like a clock winding to a stop. The Boötes Void, in this scenario, is a preview of coming attractions, a glimpse of the emptiness that awaits everything. But the measurements are not precise enough to completely rule out other possibilities. Dark energy might be slowly changing, too slowly for current observations to detect. The final verdict on the universe's fate remains open, awaiting better data and perhaps new theoretical insights. In the meantime, the Boötes Void stands as a monument to emptiness, a reminder that the universe contains not just matter and light, but vast stretches of nothing, spaces where the cosmos shows its capacity for absence. Now let us explore the practical challenges of studying the Boötes Void. Astronomy is not just about ideas and theories. It is also about the hard work of making observations, building instruments, and wrestling with the limitations of technology and nature. The Boötes Void is difficult to study for several reasons. First, it is large, very large. Surveying a region 330 million light-years across requires enormous amounts of telescope time and data storage capacity. Every observation captures only a tiny piece of the void, a pencil beam of light passing through a small fraction of its volume. Building a complete picture requires thousands of such observations, stitched together like tiles in a mosaic. Second, the void is largely empty. The things astronomers typically look for, bright galaxies, galaxy clusters, active galactic nuclei, are rare or absent within it. This means that many of the standard techniques of extragalactic astronomy do not apply. You cannot map a region using galaxies if there are almost no galaxies to map. Alternative approaches are needed, probing the void through its effects on background light or through the faint signals of neutral hydrogen and dark matter. Third, the void is located in a part of the sky that presents observational challenges. The constellation Boötes is in the northern hemisphere, making it best observed from northern observatories. But even from these locations, the void is not an easy target. It is not particularly close to any convenient foreground features that might serve as reference points. It is not particularly rich in bright stars that might be used as guide stars for adaptive optics. It is just there, a vast emptiness waiting to be explored. Despite these challenges, astronomers have made remarkable progress. The Sloan Digital Sky Survey, which operated from 2000 to 2008 in its initial phase and continues in various forms today, mapped millions of galaxies across a large portion of the northern sky. This survey provided the most detailed census yet of the Boötes Void, identifying the sparse galaxies within it and tracing the structures that surround it. Radio surveys have added another dimension. The Arecibo Radio Telescope, before its collapse in 2020, conducted studies of neutral hydrogen in the void, searching for the diffuse gas that might fill its emptiness. The results confirmed that the void contains significant amounts of neutral hydrogen, not associated with any visible galaxy, floating freely in the intergalactic medium. Infrared surveys from space have probed the void for hidden objects that might be invisible at optical wavelengths. The Spitzer Space Telescope and the Wide Field Infrared Survey Explorer scanned the region, searching for dusty galaxies, distant quasars, or other exotic sources. These surveys found some objects but nothing unexpected, nothing that would overturn our basic understanding of the void's nature. Future surveys promise even greater insights. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct a 10-year survey of the entire southern sky, visible from its location. While Boötes is a northern constellation, the observatory's data will help place the void in context, revealing how common or uncommon such structures are across the observable universe. The James Webb Space Telescope, launched in 2021, has the sensitivity to detect extremely faint objects that previous telescopes missed. If there are hidden galaxies in the Boötes Void, dim dwarf galaxies too faint for earlier surveys to find, Webb might reveal them. Early observations have not specifically targeted the void, but as the telescope's survey programs expand, the void will undoubtedly come under scrutiny. Ground-based radio telescopes are also advancing rapidly. The Square Kilometre Array, a massive international project currently in development, will have unprecedented sensitivity to neutral hydrogen across cosmic distances. When operational, it will be able to map the gas content of voids like Boötes in far greater detail than ever before, revealing whether the void is truly empty or merely dim. These technological advances will transform our understanding of cosmic voids over the coming decades. The Boötes Void, once a curiosity discovered almost accidentally, will become a well-characterized region of the cosmic web, its properties measured, and its mysteries, hopefully, resolved. But there is another kind of advance that may be equally important: advances in theory and simulation. Modern cosmology relies heavily on computer simulations to interpret observations. Scientists create virtual universes inside supercomputers, populating them with dark matter and gas and galaxies according to the laws of physics. They then run these virtual universes forward in time, watching how structures form and evolve. These simulations have become remarkably sophisticated. The largest current simulations follow billions of particles across tens of billions of virtual years, tracking the formation of the cosmic web in exquisite detail. They produce structures that look strikingly like what we observe in the real universe, including filaments, clusters, and voids. But even the best simulations have limitations. They cannot capture every physical process that affects structure formation. They must make approximations and simplifications, and they require enormous computational resources, limiting how many virtual universes can be created and how thoroughly they can be explored. One key question is whether these simulations produce voids as large and as empty as the Boötes Void. Current simulations do produce large voids, but there is some tension between the extreme properties of Boötes and what the simulations typically find. The void appears to be on the outer edge of what is expected, an unusual but not impossible fluctuation. As simulations improve, with more particles, better physics, and larger volumes, this question will be addressed more definitively. If the Boötes Void can be naturally reproduced in simulations, that will support the view that it is simply an extreme but normal feature of the cosmic web. If it cannot, that will hint at something missing from our models, whether in the initial conditions, the physics of structure formation, or something else. The interplay between observation and simulation is one of the great strengths of modern cosmology. Each informs the other. Observations revealing features that simulations must explain, simulations predicting phenomena that observations can test. The Boötes Void sits at the center of this dialogue, a test case for our understanding of the universe. Let us pause now and reflect on what we have learned. We have traveled deep into the Boötes Void, exploring its properties, its mysteries, and its implications. We have seen that the void is not truly empty, but contains sparse galaxies, diffuse gas, and dark matter. We have considered the possibility that it might harbor stranger things, from primordial black holes to the signatures of advanced civilizations. We have discussed how the void fits into the larger structure of the cosmic web and what it tells us about the physics of the early universe and the fate of the cosmos. Through it all, one theme has emerged. Emptiness is not nothing. The void is a positive feature of the universe, a region where matter is sparse but space is full, where structure is subtle but present. The void defines the cosmos as much as the filaments and clusters do. It is the silence that gives meaning to the music, the darkness that makes the light visible. And at the center of the void, hidden but not absent, we found something. Not a single dramatic object or phenomenon, but a collection of hints and clues and mysteries. Galaxies arranged in unexpected patterns, gas that never formed stars, dark matter structures invisible to our telescopes, Perhaps other things we have not yet discovered. The void holds secrets. It always has, and perhaps it always will. No matter how powerful our telescopes become, no matter how sophisticated our theories grow, there will always be more to learn. The universe is infinite in its complexity, and the void, in its profound simplicity, is part of that infinity. As we continue our exploration, let us turn our attention to some of the more profound implications of the Boötes Void. Beyond the scientific details, beyond the measurements and theories, the void raises questions that touch on the deepest aspects of human experience. Questions about our place in the cosmos. Questions about the meaning of existence itself. When we look up at the night sky, we see a universe full of light. Stars and galaxies populate our view, suggesting a cosmos brimming with activity and possibility. This perception shapes our intuitions about existence. We imagine the universe as crowded, busy, teeming with the potential for life and consciousness. But the Boötes Void tells a different story. It shows us that most of the universe is not like our neighborhood. Most of space is empty, dark, cold, devoid of the structures we associate with cosmic vitality. The galaxies and clusters and filaments are the exception, not the rule. They are islands of matter in an ocean of nothing. This realization can be unsettling. If the universe is mostly void, what does that mean for us? Are we merely accidents, brief flickers of complexity in an indifferent cosmos? Or does our existence have some deeper significance that transcends the statistical improbability of our situation? These are not questions science can answer directly. Science tells us what is, not what it means. But science can inform our reflections, providing context and perspective that shape how we think about these ultimate concerns. Consider the anthropic principle, a philosophical framework that attempts to explain why the universe appears fine-tuned for the existence of life. The anthropic principle notes that we can only observe a universe in which observers are possible. If the laws of physics were slightly different, if the density fluctuations in the early universe had different properties, if the strength of gravity or the mass of the electron were off by a tiny amount, we would not be here to wonder about it. The Boötes Void fits into this framework in an interesting way. The void is a region where the conditions were not right for abundant structure formation. Galaxies are sparse, stars are rare, and the opportunities for life, at least as we understand it, are limited. Yet the void exists, part of the same universe that produced us. This juxtaposition highlights the contingency of our existence. We are here because we happen to arise in a favorable region, a place where matter gathered and stars formed and planets coalesced and life evolved. Had we been born in the void, we would not exist. The void is a reminder of the paths not taken, the possibilities foreclosed, the countless unrealized histories that might have been. Some philosophers find this perspective troubling. If our existence is merely contingent, a matter of cosmic luck, then what grounds can we have for claiming any special significance? Are we not just momentary arrangements of atoms, destined to dissolve back into the void from which we emerged? Others find it liberating. If existence is rare and precious, a statistical miracle amid the emptiness, then every moment is a gift. The fact that we are here at all, that the universe managed to produce creatures capable of contemplating its mysteries, is a cause for wonder and gratitude. We need not appeal to external validation. Our significance lies in our capacity for experience, for understanding, for love and creativity, and the full range of human possibility. The void does not judge between these perspectives. It simply is. But in its silent emptiness, It invites us to reflect on what matters, to consider the preciousness of the filled spaces amid the surrounding dark. Let us also consider what the void might mean for the search for extraterrestrial intelligence. This is a question that has captivated humanity for generations. Are we alone in the universe? Is there other life out there, perhaps even other intelligent civilizations, with whom we might one day communicate? The Boötes Void bears on this question in several ways. First, it shows us that the conditions for life are not uniform across the cosmos. If life requires galaxies with stars and planets, then the void is not a hospitable place. Life might exist in the void's sparse galaxies, but it would be exceedingly rare, separated by vast distances from any potential neighbors. This isolation has implications for the development of intelligence and civilization. On Earth, the history of life has been shaped by competition and cooperation among species, by the exchange of genetic information, by the interconnected web of ecosystems. Intelligence emerged in this rich biological context, a product of billions of years of evolution in a teeming environment. Could intelligence emerge in the void, in a galaxy isolated from others, perhaps with fewer opportunities for biological complexity? The question is unanswerable with our current knowledge, but it is plausible that extreme isolation might inhibit the development of advanced life, reducing the chances that intelligence would arise in such regions. On the other hand, the void might offer certain advantages. Without the gravitational disturbances caused by nearby galaxies, void galaxies might be more stable over long timescales. They might provide calmer environments where life could evolve without the catastrophic disruptions that mergers and interactions can cause. Perhaps void civilizations, if they exist, are older and more developed than civilizations in crowded regions, having had more time to evolve undisturbed. These speculations lead us back to the Fermi paradox we mentioned earlier. If intelligent civilizations exist, why have we not detected any evidence of them? The void offers one possible answer. Most of the universe is too empty to support civilizations, and those civilizations that do exist in void galaxies might be too isolated to interact with or be detected by us. Alternatively, the void might be precisely where we should look for advanced civilizations. If a civilization reached Type 3 status and spread across its galaxy, then across neighboring galaxies, it might eventually fill a region of space with its technology. From our perspective, that region might appear as a void, emptied of visible galaxies as their light was captured and converted to energy. We have discussed this possibility before. It remains highly speculative, with no observational support. But the fact that we cannot definitively rule it out keeps the possibility alive in the imagination. The void invites us to consider not just what is there, but what might be there, what could be hiding just beyond the reach of our instruments. Let us now venture into some of the more recent discoveries and theoretical developments related to cosmic voids. Science does not stand still. Every year brings new observations, new insights, new questions. The Boötes Void, like all cosmic phenomena, exists in a context of evolving understanding. One recent development involves the detection of gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory made the first direct detection of gravitational waves, ripples in space-time caused by the collision of two black holes over 1 billion light-years away. Since then, gravitational wave astronomy has become a powerful new tool for studying the universe. Gravitational waves propagate through space at the speed of light, largely unaffected by the matter they pass through. Unlike light, which can be absorbed or scattered, gravitational waves pass through the cosmos with minimal interference. This makes them ideal probes of distant and obscured regions of space. Could gravitational waves tell us anything about the Boötes Void? In principle, yes. If there are sources of gravitational waves within the void, merging black holes or neutron stars, we might detect their signals. The absence of such detections could confirm that the void is truly sparse in compact objects as well as galaxies. The presence of detections could reveal hidden populations of objects that emit no light but do shake spacetime. So far, no gravitational wave events have been definitively associated with the Boötes Void. The signals detected to date have come from all directions, most from distances beyond the void. But as gravitational wave detectors improve in sensitivity and more events are recorded, the statistical distribution of sources will become clearer. If the void is truly empty of compact object mergers, that will show up as a deficit of signals from its direction. Another recent development involves studies of the intergalactic medium at cosmic dawn. Cosmic dawn is the name given to the period, roughly 100 to 500 million years after the Big Bang, when the first stars and galaxies were forming. This epoch is difficult to observe directly because it lies at the edge of what current telescopes can see. However, astronomers have begun to probe cosmic dawn using the redshifted radio signals from neutral hydrogen. Before the first stars formed, the universe was filled with neutral hydrogen gas left over from the Big Bang. This gas absorbs and emits radio waves at a specific wavelength, 21 centimeters, which has been stretched by the expansion of the universe to much longer wavelengths by the time it reaches us. By studying these signals, astronomers can map the distribution of neutral hydrogen in the early universe. They can see where gas was concentrated and where it was sparse, tracing the precursors of today's cosmic structures. These studies are revealing that the seeds of voids were planted very early. Regions that would become voids were already underdense at cosmic dawn, already beginning to lose their matter to denser neighbors. The Boötes Void, or at least the proto-void that would become it, was likely identifiable even at this ancient time. A subtle dip in the primordial sea of hydrogen. Understanding the early history of voids helps us refine our models of structure formation. It tests the predictions of our theories against observations from a completely different epoch. If the models can explain both the young voids of cosmic dawn and the mature voids of today, that is powerful evidence that we understand the underlying physics. A third recent development involves the study of weak gravitational lensing. Gravitational lensing occurs when light from a distant source is bent by the gravity of intervening mass. Strong lensing produces dramatic effects, multiple images or arcs of light around massive galaxies and clusters. Weak lensing produces subtler effects, slight distortions in the shapes of background galaxies that can only be detected statistically. By analyzing the weak lensing patterns across large areas of sky, astronomers can map the distribution of mass, including the dark matter that makes up most of the universe's gravitating stuff. This technique can probe voids directly, revealing whether they are truly underdense in dark matter or merely depleted in visible galaxies. Studies using weak lensing have confirmed that cosmic voids are indeed underdense in total mass, not just in galaxies. The dark matter follows a similar distribution to the ordinary matter, sparse in voids and concentrated in filaments and clusters. This is consistent with our models, which predict that dark matter should trace the same large-scale structure as ordinary matter. For the Boötes Void specifically, Weak lensing measurements are challenging due to the void's size and distance. Mapping the dark matter distribution across such a large volume requires enormous numbers of background galaxies to be measured with high precision. Current surveys are approaching this capability, and future surveys will likely provide detailed dark matter maps of the void and its surroundings. Let us also consider the implications of the Boötes Void for our understanding of dark matter itself. We have mentioned that the void is underdense in dark matter, but this raises interesting questions about dark matter's properties. In the standard model, dark matter consists of particles that interact only through gravity and possibly through the weak nuclear force. These particles, called WIMPs for weakly interacting massive particles, would cluster gravitationally in much the same way as ordinary matter, just without the additional interactions that cause ordinary matter to form stars and planets. But there are alternative models of dark matter that predict different behavior. Some models propose that dark matter particles can interact with each other, producing effects that would modify how dark matter clusters. Others propose that dark matter is not made of particles at all, but consists of more exotic objects, such as primordial black holes or topological defects in spacetime. The distribution of dark matter in cosmic voids can help distinguish between these models. Different dark matter candidates would leave different signatures in how voids form and evolve. By measuring the dark matter content and structure of voids with increasing precision, astronomers can test these predictions and narrow down the possibilities for what dark matter actually is. The Boötes Void, as an extreme environment, is particularly valuable for these tests. Any differences between dark matter models would be most pronounced in extreme conditions, where the density is very low or the scales are very large. The void provides a natural laboratory for probing dark matter in regimes that are difficult to study elsewhere. Another area of active research involves the possible connection between cosmic voids and the quantum vacuum. In quantum field theory, the vacuum is not truly empty, but seethes with virtual particles, pairs of particles and antiparticles that pop into existence and annihilate almost immediately. This quantum vacuum has energy, and that energy might be related to the dark energy that drives the accelerating expansion of the universe. The connection between quantum vacuum energy and dark energy is one of the great unsolved problems in physics. Naive calculations suggest that the quantum vacuum should have far more energy than we observe, off by a factor of 10 to the 120 power, perhaps the worst prediction in the history of science. Clearly, something is missing from our understanding. Cosmic voids might offer clues to this puzzle. If dark energy is related to the quantum vacuum, and if the properties of the vacuum depend in some way on the local environment, then voids might behave differently from dense regions. The void might be a place where the vacuum has different properties, where dark energy manifests differently, where new physics might be observable. This is highly speculative territory at the frontier of theoretical physics, but voids, like Boötes, provide motivation for these speculations. They show us environments unlike anything in our immediate cosmic neighborhood, pushing the boundaries of where our theories have been tested. As our journey through the void continues, let us take a moment to appreciate the human dimension of this story. Science is not just about facts and theories. It is about people, curious individuals who devoted their lives to understanding the universe. The discovery of the Boötes Void in 1981 was the work of a team led by Robert Kirshner, an astronomer who has made many important contributions to our understanding of the cosmos. Kirshner and his colleagues were conducting a survey of galaxy redshifts, measuring how fast galaxies were moving away from us to determine their distances. This was painstaking work, requiring hours of telescope time to measure the spectrum of each galaxy. When the team analyzed their data, they noticed something strange. In a particular region of sky, the galaxies seemed to drop out. There were almost none at certain distances, as if a great chunk of the universe had been scooped away. Further observations confirmed that this was not a statistical fluke or an error in the data. The void was real. The discovery sparked immediate interest in the astronomical community. Nothing like the Boötes Void had been seen before. It challenged prevailing ideas about the distribution of matter in the universe and opened new questions about cosmic structure formation. In the decades since, hundreds of scientists have contributed to our understanding of the void. They have mapped its boundaries, catalogued its sparse galaxies, searched for hidden gas and dark matter, and developed theories to explain its origin and properties. Each researcher has added a piece to the puzzle, building on the work of those who came before. This collaborative nature of science is one of its great strengths. No individual could hope to understand the Boötes Void alone. It requires the combined efforts of observers, theorists, instrument builders, computer programmers, and many others, working across institutions and nations and generations. The void is a testament to what humanity can accomplish when we work together in pursuit of knowledge. And the work continues. At this very moment, astronomers are observing the void with the latest telescopes. Theorists are running new simulations, testing new models, asking new questions. Students are learning about the void for the first time, perhaps finding in it the spark that will ignite their own scientific careers. The void has become part of our collective intellectual heritage, a landmark in our map of the cosmos. It will continue to be studied, debated, and wondered at for as long as humans gaze up at the stars. The cosmic environment. Voids that formed in regions of weak gravitational influence tend to be more spherical. Those that formed near massive structures tend to be more distorted, their shapes molded by the gravitational pull of their neighbors. By measuring void shapes statistically, astronomers can probe the distribution of mass on large scales, complementing other techniques like galaxy surveys and weak lensing. The Boötes Void appears to be relatively spherical compared to many other voids. This is consistent with its location in a region of relatively uniform surrounding density. The void has not been strongly pulled or distorted by any single dominant neighbor. It has been able to expand roughly equally in all directions, approaching the ideal spherical form. Other notable voids have their own stories to tell. The local void, which lies relatively close to our own galaxy, is a modest underdensity that nonetheless affects the motions of nearby galaxies, including the Milky Way. The Eridanus supervoid, associated with the CMB cold spot we discussed earlier, has sparked debates about its size and properties. The Giant. Void discovered by astronomers Rudnick, Brown, and Williams is another large underdensity that has attracted attention. Each void provides a data point, a sample from the distribution of cosmic environments. Together, they build a statistical picture of how the universe is structured on its larger scales. The Boötes Void, as an extreme member of this population, helps define the upper limit of how empty space can become. This statistical perspective is important because it helps us distinguish between explanations for unusual features like Boötes. If the void is simply an extreme fluctuation, an outlier in the distribution of void properties, then we should be able to find it at the tail of the distribution we measure for all voids. if it cannot be accommodated by the distribution, if it is too large or too empty to fit, then we must look for special explanations. Current data suggests that the Boötes Void is extreme but not impossible. It lies at the edge of the expected distribution, an unusual but statistically plausible outcome. This supports the view that no special physics is needed to explain it. The void is strange, but the universe is large enough that strange things happen. Yet this conclusion is not entirely settled. As we gather more data on cosmic voids, as our surveys become more complete and our measurements more precise, the picture may change. Perhaps we will find other voids as large as Boötes, confirming that such structures are rare but expected. Or perhaps Boötes will remain unique, a singular anomaly that demands explanation. The search continues. Every new survey, every new telescope, every new analysis brings us closer to a definitive answer. The void waits, patient and silent, for us to understand its secrets. Let us also consider the philosophical implications of cosmic scale itself. The Boötes Void is 330 million light-years across. This number, like most astronomical distances, is essentially meaningless to human intuition. We evolved on a planet where the largest distances we naturally encounter are a few thousand kilometers. Our brains are not equipped to grasp what a light-year means, let alone hundreds of millions of them. And yet we try. We build mental models, use analogies, create visualizations. We shrink the universe to human scale in our imaginations, making the incomprehensible comprehensible. In doing so, we participate in one of humanity's greatest intellectual achievements, the extension of our understanding beyond the limits of our senses. The void challenges this understanding in a particular way. It confronts us with emptiness, with absence, with nothing. Our minds are naturally drawn to things, to objects we can name and describe and manipulate. Emptiness is harder to grasp. It has no features to anchor our attention, no landmarks to guide our exploration. But the void is not truly nothing. It is space, the same space that exists everywhere in the universe. It has properties, it expands, it curves in response to mass and energy. It carries the quantum fields that underlie all physical phenomena. The void is not the absence of existence. It is a particular mode of existence, one defined by sparsity and isolation, rather than abundance and connection. In this sense, the void is as real as any other part of the cosmos. It is not a hole in the universe, but a region of the universe with specific characteristics. It has boundaries, an interior, a history, a future. It participates in the cosmic evolution, draining and expanding and evolving with the passage of cosmic time. Perhaps the void can teach us something about the nature of reality itself. In our daily lives, we tend to identify reality with stuff, with material objects that we can see and touch and measure. But physics tells us that space itself is as real as the objects within it. The void, precisely because it contains so little matter, reveals the reality of space more clearly than regions filled with galaxies and stars. Einstein showed us that space and time are not merely the stage on which physics plays out, but active participants in the drama. Space can curve and stretch and warp. It can expand, carrying galaxies apart, like raisins in a rising loaf of bread. The void, with its profound emptiness, is a place where we can contemplate space for its own sake, undistracted, the busy activity of matter. This contemplation connects to deep questions in philosophy and physics. What is the relationship between space and the objects that inhabit it? Could space exist without any matter at all? Does the void have intrinsic properties, or is it defined only by what it lacks? These questions have been debated for millennia, from the ancient Greek atomists who imagined atoms moving through a void to the modern physicists who struggle to reconcile quantum mechanics with general relativity. The Boötes Void does not answer these questions, but it provides a concrete example to focus our thinking. It is a real void, not an imagined one, and whatever we conclude about the nature of space must apply to it. Now let us journey toward the conclusion of our exploration. We have traveled far, from the night sky visible above Earth to the farthest reaches of cosmic structure. We have explored the Boötes Void in depth, examining its properties, its mysteries, and its implications. What have we learned, and what remains to be discovered? We have learned that the void is vast, one of the largest known structures in the observable universe. Its 330 million light-year diameter dwarfs anything in human experience, stretching across cosmic distances that light itself takes hundreds of millions of years to traverse. We have learned that the void is largely, but not completely empty. It contains perhaps 60 galaxies where 2,000 would be expected, sparse islands of matter in an ocean of dark. These galaxies are isolated, pristine, untouched by the cosmic traffic that shapes galaxies elsewhere. They offer windows into galactic evolution in its purest form. We have learned that the void contains more than meets the eye. Diffuse gas, invisible to optical telescopes, but detectable at radio wavelengths, fills some of its volume. Dark matter, detectable only through gravity, provides an invisible scaffold that shapes the void's structure. The void is not nothing, but something, a region of space with its own complex properties. We have learned that the void fits, if barely, within our current understanding of cosmic structure formation. It represents an extreme outcome of the gravitational instability that shapes the universe, a rare fluctuation at the tail of the distribution. No special physics is required to explain it, though its existence pushes our theories to their limits. We have learned that the void raises profound questions about the nature of the cosmos and our place within it. It reminds us that the universe is not made for human comprehension, that most of space is empty and dark and indifferent to our concerns. Yet it also invites wonder, challenging us to find meaning in the face of cosmic vastness. What remains to be discovered? Much, undoubtedly. Future telescopes will map the void in greater detail, revealing structures and features that current instruments cannot detect. Future theories will refine our understanding of how the void formed and evolved, testing our models against the most extreme cosmic environments. Perhaps we will discover that the void harbors secrets we have not yet imagined, new populations of objects, new physical phenomena, new clues to the deepest mysteries of existence. The void is large enough to contain many surprises, and science has a long history of finding unexpected things in unexpected places. Or perhaps we will confirm that the void is exactly what it appears to be, an unusual but comprehensible feature of the cosmic web, an extreme example of processes we already understand. This would be a triumph of scientific understanding, a demonstration that our theories can explain even the most challenging observations. Either outcome would be valuable. Science advances both through discovery and through confirmation. The void will teach us something either way. As we conclude our journey through the Boötes Void, let us return to the question that began this exploration. We found something hiding in the void, and it should not be there. What did we find? We found galaxies, sparse but present, arranged in patterns that surprised us. We found gas, diffuse and ancient, never condensed into stars. We found the imprint of the early universe, quantum fluctuations amplified to cosmic scales, shaping emptiness as surely as they shaped abundance. We found the interplay of gravity and expansion, matter and void, structure and absence. And we found ourselves, our curiosity, our wonder, our determination to understand. The void is empty of matter, but it is full of meaning for creatures like us, who ask questions about the cosmos. In looking outward at the void, we look inward at our own nature as seekers of truth. The universe is not obligated to make sense to us. It is not required to conform to our expectations or satisfy our desires for meaning. But somehow, despite its vast indifference, the universe is comprehensible. Its laws can be discovered. Its structures can be mapped. Its mysteries can be explored, if not fully solved. This comprehensibility is itself a mystery, one that philosophers and scientists have pondered for generations. Why should the universe be understandable at all? Why should mathematics, a human invention, describe the behavior of stars and galaxies billions of light years away? Why should creatures evolved on a small planet have any insight into the workings of the cosmos? The Boötes Void does not answer these questions, but it embodies them. It is a test case for our understanding, a challenge to our theories, a frontier for our exploration. In confronting the void, we confront the limits of human knowledge and the possibilities for extending those limits. The void is out there, waiting. It has waited for billions of years, since long before Earth formed, since long before life began, since long before any mind arose to contemplate its existence. And it will wait for billions of years more, expanding slowly as the universe grows, draining gradually as the last vestiges of matter fall away. In that cosmic patience we find both humility and inspiration. The void does not need us. Our observations, our theories, our explorations, all of these are momentary flickers in the long history of the cosmos. But for us, for creatures whose lives span mere decades in a universe of billions of years, the void matters enormously. It is part of our inheritance as conscious beings, a feature of the universe we are privileged to know. And in the deepest nothing of the cosmos, there is always something to find. That something might be matter, sparse and isolated, but present. That something might be physics, the laws that govern emptiness as surely as they govern abundance. That something might be meaning, the significance we create as thinking beings contemplating the infinite. The void is not empty after all. It is full of questions, full of possibilities, full of the infinite potential of an unknown frontier. And we, standing on our small world, at the edge of the Milky Way, have the privilege of looking into that darkness and wondering what lies within. So gaze upward on a clear night. Find the constellation Boötes, following the arc of the Big Dipper to the bright star Arcturus. Know that beyond those visible stars, beyond the familiar patterns of our night sky, lies a vast emptiness stretching for hundreds of millions of light years. Know that this void is real, mapped, and measured by human ingenuity, yet still mysterious in its depths. And know that in looking at the void, you are participating in humanity's greatest adventure. The quest to understand the universe, to find our place within it, to discover what hides in the darkness. This quest has no end. There will always be more to learn, more to explore, more to wonder at. The void invites us onward, into the emptiness, into the unknown, into the endless mystery of existence itself. Rest now beneath the stars. Let the cosmic silence embrace you. Let the vast distances between the points of light remind you of the scale of all that is. And know that even in the deepest void, Even in the farthest reaches of the cosmos, there is always something waiting to be found. The universe, it seems, is full of surprises, even in its emptiest reaches, especially in its emptiest reaches. And that is perhaps the greatest mystery of all. Before we close this chapter of our cosmic voyage, let us linger a moment longer in the contemplation of what the Boötes Void teaches us about the architecture of reality. The universe, at its most fundamental level, appears to be built on contrast, light and dark, matter and void, presence and absence. These dualities are not merely descriptive, they are constitutive. The cosmos would not be what it is without both terms of each pair. A universe of pure light would be no universe at all. A cosmos without void would have no structure, no web, no differentiation between here and there. The Boötes Void embodies this principle of cosmic contrast. It exists because the filaments and clusters exist. Its emptiness is defined by their fullness. The void is not nothing set apart from the something of the cosmic web. It is an integral part of that web, the negative space that gives the positive structures their definition. This interdependence runs deeper than mere geometry. The physics of the void and the physics of the filaments are the same physics. Gravity, dark matter, dark energy, the expansion of space, all of these operate in the void just as they operate elsewhere. The difference lies only in the initial conditions, in the primordial fluctuations that seeded structure in some places and sparseness in others. In a sense, the void and the filaments are siblings, born of the same cosmic parent. The quantum fluctuations of the early universe, stretched to cosmic scales by inflation, became the blueprint for all that followed. Some parts of that blueprint called for density, other parts called for emptiness. The Boötes Void is simply following the instructions written into the fabric of space-time nearly 14 billion years ago. This perspective invites us to see the void not as an anomaly, but as a natural expression of cosmic creativity. The universe could have been uniform, the same everywhere, no structure, no variation, no differentiation. Instead, it chose to be diverse. It created places of abundance and places of scarcity, places where matter gathered and places where it dispersed. The void is evidence of this choice, testimony to the universe's capacity for variety. Why did the universe choose variety over uniformity? This is a question that physics cannot fully answer. The laws of physics permit both outcomes. A perfectly uniform universe would obey the same equations as our structured cosmos. The difference lies in the initial conditions, in the state of the universe at its beginning. Cosmologists believe that those initial conditions were set during inflation, the brief period of explosive expansion in the first fraction of a second. During inflation, quantum fluctuations were amplified and frozen into the fabric of space. These fluctuations were random, distributed according to the probabilistic rules of quantum mechanics. They could have been different. In some sense, they were chosen by chance, a cosmic roll of the dice that determined the structure of everything that followed. If this picture is correct, then the Boötes Void exists because of a quantum fluctuation that occurred almost 14 billion years ago. A fluctuation that lasted far less than a second. A fluctuation so small that it would be entirely imperceptible at human scales. Yet that fluctuation determined the fate of a region of space 330 million light-years across. It ensured that this region would be sparse while neighboring regions would be dense. It wrote the story of the void before any of the characters had been created. This is the strange temporality of cosmology. Effects can be traced back to causes that occurred at the beginning of time. The present state of the universe is a consequence of its initial state, mediated by the laws of physics that govern cosmic evolution. The void we see today is not separate from the void that was seeded at the Big Bang. It is the same void, evolved over billions of years, still following the trajectory set in those first moments. Understanding this connection between origin and outcome is one of the great achievements of modern cosmology. We can look at the cosmic microwave background, the oldest light in the universe, and see the seeds of structures like the Boötes Void. We can trace the development of those seeds through cosmic time, watching in simulations as voids form and grow and empty out. We can predict what the void should look like today and compare those predictions to observations. The agreement is remarkable, a triumph of human understanding over cosmic mystery. Yet mysteries remain. The initial conditions themselves remain unexplained. Why did inflation happen? Why did it produce the particular pattern of fluctuations that it did? Why does the universe exist at all? These questions take us beyond physics into metaphysics, into realms where observation and experiment can't yet reach. The Boötes Void does not answer these ultimate questions, but it holds them. It is a physical embodiment of cosmic contingency, a reminder that the universe could have been otherwise. In its vast emptiness, we see the consequences of primordial chance. We glimpse the moment when the dice were rolled and everything that would ever be was determined. This glimpse is both humbling and exhilarating. Humbling because it shows us how small we are, how little our choices matter in the cosmic scheme. The void does not care about us. It would be there whether we existed or not. Our observations do not change it. Our theories do not affect it. It simply is a fact of the universe that we can acknowledge but cannot alter. Exhilarating because it shows us how much we can understand. Despite our smallness, despite our brief existence on a single planet in a single galaxy, we have figured out the story of the void. We know how it formed, why it is empty, what it is made of and not made of. We have reached across billions of light years with our minds and grasped something of the truth. This capacity for understanding is itself a cosmic phenomenon, as remarkable in its way as the void itself. Somewhere in the universe, matter arranged itself into beings capable of comprehending the whole. We are those beings. The void is part of our inheritance, a mystery we were born to explore. The night sky, to human eyes, appears as a dome of darkness punctuated by points of light. This appearance is misleading. The sky is not a dome but a window, an opening onto infinity. Through that window, we see the Milky Way, our home galaxy. We see other galaxies, other stars, other worlds. And we see, if we look with the right instruments and the right understanding, the voids that fill most of the cosmic volume. The Boötes Void cannot be seen with the naked eye. It is too far away, too empty, too lacking in the bright objects that catch our visual attention. But it is there, as real as anything we can touch or taste or hear. It is part of the universe we inhabit, part of the story we are trying to tell. What will we discover about the void in the years and decades to come? No one can say for certain. Science is full of surprises, and the universe has a habit of defying our expectations. Perhaps we will find that the void contains hidden structures we never suspected. Perhaps we will learn that it plays a role in cosmic processes we do not yet understand. Perhaps we will simply confirm what we already believe, filling in details and refining measurements without overturning our basic picture. Whatever we discover, the search itself is worthwhile. The void invites us to look, to wonder, to ask questions about the nature of existence. It challenges us to expand our minds beyond familiar horizons, to contemplate distances and timescales that dwarf our everyday experience. It offers us a glimpse of the universe's true scale, reminding us that we are small, but not insignificant. For in our smallness, we contain multitudes. In our brief lives, we reach for eternity. In our limited understanding, we touch the infinite. The void, for all its emptiness, is full of the meanings we bring to it. It is a canvas on which we paint our questions, a mirror in which we see ourselves reflected against the cosmic dark. The journey continues. The void awaits. And somewhere in that great emptiness, hidden but waiting to be found, are the answers to questions we have not yet learned to ask. Sleep well beneath the stars. Dream of voids and filaments, of galaxies and space. Tomorrow brings new observations, new theories, new chances to understand. The universe is patient. It has been here for nearly 14 billion years. It will be here for billions more. And we will be here too, for as long as we can manage. Looking up, wondering, seeking, finding something always in the deepest nothing.